Hi everyone, my name is MAvis. I'm a computer engineering student at CSU. I'm taking ECE 311 and 331, not 341. For Knowledge Integration 2, we're discussing the audio backend system. So essentially this is an audio amplifier, a two-stage amplifier whose purpose is to take an input signal and amplify it in two stages before sending it to a speaker as an output signal. Given the assumption that the audio amplifier is an LTI system, and also given an input signal, we can find a general equation for the output signal. We use the frequency response h of j omega, and the output signal can be expressed as these two equations, which are equivalent. So as you can see, the output signal looks very similar to the input signal, except it is amplified by the magnitude of hj omega naught, and then the phase of hj omega naught is added to the input phase. We simulated this circuit through Cadence, and you can see the simulation results here. The red line is the input voltage set at 10 millivolts. The green line is the output voltage, and the blue line is V in or V out over V in, so or the gain of the circuit, which is also in this case the frequency response. The cutoff frequency, where the gain is half of the original, right, so the -3 decibel level, was found to be just a little over 5 megahertz. These plots show the frequency versus frequency response for both magnitude and phase. So again, as the input frequency increases, the frequency response, so the gain, decreases. And that's for magnitude. Similarly, for phase, as you increase the input frequency, your output phase becomes more and more negative, so it's becoming less and less in phase, so more and more out of phase with the original input signal, which you want them to be the same phase. So given a sample input signal, we use a periodic square wave. We can use Fourier analysis and find the Fourier coefficients to approximate an input signal, as shown here for the first 50 harmonics. So square wave can be represented as a sine wave using Fourier analysis here. Using this also, you can find the output signal, which again looks similar to the input signal we found, only magnified or amplified by the frequency response. Interestingly, the output does look like the input signal, but because the square wave is not a linear system or a linear function, the output must be. So it does look like a square wave. However, there are ripples at each rising and falling edge, which is known as the Gibbs phenomenon. Shown here is what the output would look like with those ripples. Analyzing the circuit with small signal analysis, you can also find the small signal quantities, transconductance, and output resistance for each transistor. Interestingly, the transconductance of the second transistor, the stage 2 transistor, is much higher than the first one, which means that the output to input ratio for current through the transistor is very high, and we'll get to what that means here in a couple slides. So discussing linear region versus saturation region, if you input too high of an amplitude signal as the input to this system, the system goes from saturation region, which is its normal operating mode, to the linear or triode region, meaning the system will no longer function as it's intended to as an amplifier. So the gain will be reduced, and your output signal will no longer completely match the input signal. So yeah. The reason that this system has two transistors, so why it's a two-stage amplifier, is because the first stage amplifies the input signal, the input voltage, to an acceptable level, but it doesn't actually do anything with the current. So at the output with the speaker, it has such a low resistance, low load resistance, that amplified voltage is not enough to, doesn't give it enough power to amply drive the speaker. So the second stage is added in, and it amplifies the current from the first stage so that there is adequate power, and then combining both stages makes it so that there's relatively high gain between the low input signal and the desired output signal. So that is that for Knowledge Integration 2. Thank you for watching.